Hello everyone. Thank you for this invitation and introduction. I am Dr. Suhas P Veetil from Higher Colleges of Technology, Dubai, United Arab Emirates. I would like to present our results on depth resolved imaging by digital holography via an alternative technique called sample shifting. Three-dimensional imaging offers number of benefits and it has facilitated advancements in biological and material sciences. A variety of techniques have been developed in recent past to create 3D images of the object. There are popular approaches like confocal optical coherent tomography, structured illumination, and digital holography. Each one has its own advantages and disadvantages, limitations. If you look at the confocal approach, it relies on point-to-point scanning in the XYZ space. This makes the data collection process time-consuming. Optical coherent tomography can give very good resolution, and it is also much faster than confocal technique, while it uses spectral interference and two-dimensional mechanical scanning. And when it comes to structural illumination, it uses pre-designed carrier frequencies to illuminate the surface of the object, and it generates highly modulated deformed fringe images which are captured by imaging equipment at different viewing angle. And then the 3D image of the object is then reconstructed by digital demodulation. But here it is crucial to distinguish the high frequency information modulated by the object surface from its background. So this poses a limitation with complicated structures. In digital holography, we are able to reconstruct an object's quantitative phase and modulus, including depth information. And the image created by digital holography is essentially by digital defocusing. It's just a superposition of clearly focused image and many defocused images. And hence, it cannot reliably convey the 3D information about the object being viewed. So to overcome such limitations, several modifications have been proposed in recent years. So this includes either rotating the object or changing the angle of incidence of the illumination or continuously changing the wavelength of light during the recording. However, the complexity of the experimental implementation of such approaches places restrictions on many applications. So here we propose an alternative technique to obtain depth resolved imaging by laterally shifting the sample in digital holography. The reflected light from the sample is made to interfere with a plane reference beam and it forms a digital hologram. The holograms are recorded while shifting the sample. An algorithm selectively generates the modulus and phase images of the object at different focal depth. A typical holographic setup is used to accomplish the suggested approach, and a single distribution of illumination is needed for computation, which can largely reduce the amount of collected data. So let's look at the theory of the experiment. So we assume the sample is made up of numerous optical slices along the axial direction as shown in the diagram on the right side. So they are illuminated by spherical wavefront originating from the point source O. The transmission function of this transparent sample can be expressed by the following expression Txy, where M represents several layers, and each layer, each slide satisfies the following conditions. So where the phase angle is much less than pi, and also the transmission is nearly equal to 1. And we obtain the reflected light from all layers of the sample by the following expression Rxy from all layers. And this exponential function that represents the complex amplitude distribution of the illumination on the mth layer. N0 is the refractive index, and Zm represents the distance between the point source and the mth layer along the axial direction. The overall reflection from the sample can be further simplified as an integral as shown here, Rxy, and we obtain the reflected light from a particular layer called kth layer. It's obtained by removing the illumination on the kth layer, and we modify this as R dash xy. And when the wavefront illumination on the sample is continuously varied by shifting, as in the proposed method, the overall reflection may be described by adding up all the R dash xy. We obtain R double dash xy. And here this L, capital L, denotes the overall number of illuminations. And look at the final simplified expression. So which is non-zero at the kth layer, and making it effectively the sample's kth layer reflection function, which is taken from overall number of illuminations. Now let's discuss the experimental setup. We use a typical holographic setup for this experiment. So we have this beam splitter which splits the laser beam, divides into two. One acts as a reference beam, pass through the spatial filter, and the second one pass through the sample. So the first one acts as a reference beam, and the other one as a spherical wave that illuminates the sample. And here you can see the prism which combines both beams and creates a hologram which is captured on a CCD. And here the sample is fixed on a shifting stage, and it equidistantly shifts in the x direction. And we can obtain the illumination on the front surface using a reflecting surface. So this can be done in advance. And the illumination on inner layers can be achieved by propagating the light to the inner layers using Fresnel diffraction formula. The figure shows the hologram recording on the front surface of the sample, which is the illumination, and B and C shows the reconstructed modulus and phase images obtained from the hologram. So we have used a sample to explain the features of our experiment. So we used a glass plate with a thickness of 1.8 millimeter, and microscopic structures are engraved on this glass plate, which has a diameter of about 200 micrometers, and with a width of the scratch line having a width of around 30 micrometers. So this microscopic images shows the microstructures on the front and rear surfaces. So it represents two layers of a sample at a depth having a thickness of 1.8 millimeter. So every time the sample is shifted by around 9 micrometers in the x direction, and we record a hologram. So this shifting continues, and we have recorded around 111 holograms, and it took almost 40 seconds to complete the recording of 111 holograms. So here the pictures C and F shows the hologram that was obtained after 21st shift and 71st shift out of 111 shifts. So these two holograms. What you can notice here, after reconstruction, you can see an obvious crosstalk, and also you can see that the hologram is shifted. So this is because of the shifting. This is one. The first one represents 21st shift, and the second one is 71st. So since it is shifted, you have to have a benchmarking. So you take as a reference. So the reference is taken as the hologram, which is obtained after 55th shift, and then we calculate everything based on that benchmark, and that benchmark region is shown by the white rectangle here, and this shows the reconstructed images of front and rear surfaces obtained by the reconstruction of the hologram. As you can notice, there is only negligible amount of crosstalk between the front and back surface, or front and rear surface. So which shows the effectiveness of our method to obtain depth result imaging. And we also looked at the resolution using resolution target films. And again, it is used on the front and rear side. On the front side, we use this target, and on the other side, we use some random squares distribution. While examining the resolution target, those group elements, we understood that the resolution along the x direction is around 13.9 micrometers, and resolution in the y direction is about 22.1 micrometer. So I would like to conclude now. So we have used single wavelength digital holography for depth result imaging. It is achieved by shifting the sample in equal intervals while keeping the illumination unaltered. Proposed a technique to obtain the complex reflection function at a particular layer by holographic reconstruction. And experimental setup is simple with a fewer data acquisition along with the adjustable field of view. And this method is suitable for 3D imaging of highly transmitted samples. Thank you for your time.